Hello, welcome back to our journey into matrices. Today we're going to look at determinants of matrices. If you've never heard that word before, don't panic. I'm going to explain what it is, and we're going to be doing a lot of calculations of determinants. So, as we go along, we'll talk a little bit more about matrices. Now, previously, you had used matrices, in a previous video, you had used matrices to basically have another method for solving systems of linear equations, because we used them to set up an augmented matrix and then used either Gauss-Jordan elimination or Gaussian elimination to help us with finding our solutions to the systems. But today we're going to look at another technique, some more techniques. But before we do, we're going to first talk about what a determinant is and how to find it. Okay, one of the keys with determinants is that we're dealing with square matrices. So in other words, the number of rows and the number of columns is the same. And that's very specific. We're dealing with square matrices when we do this particular thing of finding determinants. And although you can do these in graphing calculators, like in Desmos, I'm not going to demonstrate that because, like, on your test, you're going to need to be able to work it out yourself. But if you want to try to do it in Desmos has a matrix calculator, super easy to use. If you're not sure, you can always Google real quickly how to use it. Anyways, okay. So let's go back to talk about determinant. Let's start with a 2 by 2 matrix. Okay, so they like to use capital letters a lot when naming these matrices. And I'm not going to actually put the elements in there just yet, but I'm going to put these little letters to represent the elements, and then the numbers tell you row and column location of that element. So like 1, 1 means row 1, column 1. 1, 2 means row 1, column 2, etc. Then 2, 1 is row 2, column 1. 2, 2 is row 2, column 2. Okay, so that's the matrix A. The determinant looks like the absolute value symbols. So if you put little absolute value symbols around A, the name of the letter for the matrix, you can put absolute value symbols around the actual matrix instead of the little brackets, and that's saying, hey, we're doing determinant right now. And it's found by doing this crisscross sort of multiplication and subtraction. You're going to take A11 and A22, you're going to multiply those two together. And you're going to take A21 and A12 and multiply those together. And you're going to subtract the results. So you have that little diagonal multiplication starting from the upper left at A11, first row, first column. You'll start there, do a little diagonal multiplication, and then do the other diagonal multiplication and subtract the results. And that's it for a 2 by 2 matrix. That is your determinant. So let's say that, for example, you have matrix B that has numbers 5, 2, and then -8, -4. And you're asked to find the determinant of B. So you know you're finding the determinant because of the little absolute value symbols. And so we're going to take our array of numbers named B there, that matrix, and we're going to find a single number called that determinant. So we're going to take 5 and -4 and multiply those together. So we want to take this diagonal, and then we're going to subtract when we take the other diagonal and multiply those together, the 2 and the -8. So we end up with -20 minus -16, and that gives you -4. So -4 is considered to be the determinant of matrix B there. All right. Now you might be looking at that and going, all right, that's cool and all, but what's the point? Well, the point will help you down the road, especially most of you are probably thinking about taking calculus. So determinants are used in calculus to find something called vector cross products. And those are used to help study different forces, like in sciences such as physics or in aerospace engineering or space, astrophysics, stuff like that. So a lot of scientific applications, especially if you're going on to calculus. Okay, let's move on to a 3x3. Let's have some fun there. Okay. Let's say you have a 3x3 matrix. We'll call it A again. They like to use letter A or letter B. So you have, we'll use little a's for the elements. And again, the little numbering system for row, column. So first number is the row, second number is the column it's in. All right. Now if we're wanting to find the determinant of this matrix, we have to take the diagonals again. We have to multiply the numbers in the diagonals. And then what we're going to do is for the same diagonals, we're going to add up the results. And then for opposite diagonals, we're going to subtract. I know that sounds a little weird, what I'm saying there, but okay. But hopefully I can use some different colors and make it make sense. All right, so we would take A11, A22, and A33 and multiply those together. Then we're going to look at another diagonal going that same kind of direction. We're going to look at A12, A23. And if you pictured this matrix being like stamped over and over next to itself and under itself and over itself, you would be able to see where the diagonal goes easily. But I don't have time to sit and try to do that. I don't have the graphics type knowledge to make a pretty little graphic to do that. So just trust me that this would end up touching that piece there. So that would be the A31 would be part of that same diagonal. So A12, A23, and A31 will get multiplied together. And then that last diagonal, yeah, you have A13 up here in this corner, and it would end up touching with the A21, A32. Okay, so those diagonals, you add them up. And then just like in the previous, the 2x2, you're going to end up subtracting the results. So now we're going to go the other direction. I'm kind of limited on colors, sorry about that. But we're going to look at the diagonal this way, the A31, A22, A13. And then we're going to add with that, like we're going to look at all the diagonals going that way. So you have A32, A23, and then that would loop around to A11. And what color have I not used yet? I already used blue, pink, green, or I think I've used all my different color options here. Guess I'll just use black. All right, and then we've not done A33 with A21 and A12. So A21 and A12 gets to go with A33. Okay. So let's say you had a nice little matrix with numbers. Like, how would that look? Okay, I have a matrix. I went ahead and named it C. And it has the numbers 5, -1, and 6 in row 1. It has 0, 2, -9 in row 2, 4, 1, and 3 in row 3. And I'm determined to find the determinant of C. Okay. So I would do 5 times 2 times 3 plus I would do -1 times -9 times 4 plus I would also do 0 times 1 times 6. And then I'll be subtracting. And then I gotta do, try and keep it all straight here. 4 times 2 times 6. And then I gotta also do 1 times -9 times 5. And then finally, I gotta do the 0, the -1, and the 3 together. All right, so 5 times 2 is 10, 10 times 3 is 30. -1, -9 is 9, 9 times 4 is 36. Then I got a 0. Then I gotta subtract. 4 times 2 is 8, 8 times 6 is 48. Then I got -9 times 5 is -45, and then another 0. So I've got, what, 66 minus 3. And that gives me 63. So there's your determinant for that 3 by 3 matrix. Now in your book, you can go in and as you read the lesson, it goes through and shows you that this process that I just, wrote out above in generic terms and then did an example of with numbers, you can do a little bit of algebra and make this look a little different. Like if you look up at the top of this page there, you'll notice that some of those multiplications have common factors. And you can actually go through and factor out things. Like, let's say you focused on the first column. So on A11, A21, A31. You could go in, you could factor out A11 in certain situations. Wherever you see A11, you could factor that out. Wherever you see A21, you can factor that out. And wherever you see A31, you can factor that out. Do a little bit of algebraic manipulation, and an interesting pattern comes out of this. And this pattern might make it easier to keep everything organized as you find these determinants. Like the way I just did it, finding that determinant is doable, it works. But honestly, trying to keep track of where everything is with the diagonals can be a little tricky. So what's another way to look at that? Okay, let's say you factor A11 out of, let me go back to writing in black, sorry. Let's say you factor A11 out of its terms. You end up with A22, A33 minus A3, 2, A2, 3. And then you have a minus A2, 1 you can factor out. So then you have A1, 2, A3, 3 minus A3, 2, A1, 3. And then you have a plus A3, 1 you can factor out. And then you're left with A1, 2, A2, 3 minus A2, 2, A1, 3. If you look back at the original matrix, sorry, it just takes forever to write some of this stuff out, doesn't it? Maybe in the future I'll be able to create some slides so I don't have to do so much writing when I make these videos. All right, let's look at the A11 situation first. You've got A11 right here. Well, A22 and A33 get multiplied together. A32 and A23 get multiplied together here. And then you subtract the results. Well, that's the same thing as finding the determinant of that little matrix. The determinant of each of those little 2 by 2 matrices is called the minor of that associated element in the 3 by 3 matrix. So we have our minor of M, so M11, minor of A11 is that determinant. It's that A22, A33 minus A32, A23. Okay, what about that other situation with the A21? Let me rewrite the matrix real quick. So looking at A21, the A12 and the A33. So you're taking this one and this one, multiplying them together, and the A32 and the A13. So notice something. You end up, once you are looking at a certain element in the matrix, you're ignoring all of the elements in that same row and column and then finding the determinant of the 2 by 2 that's left over. Like even in that first example, when we did this earlier, back with the A11, we ended up ignoring all the elements in that first row and first column where A11 was located. And just looking at the 4 elements left over. Okay, so the minor 2-1, M21, or the minor of A21 is that A12, A33 minus A32, A13, and so on. Okay. You can go through and do that for each of the elements. You can go through and do it for A31 next if you want to. Depending on how you factor, you could end up picking any row or any column in your matrix and factoring based on the elements in that row or that column and finding these minors. So I mean, I ended up choosing all these elements in the first column. But let's say I wanted to choose all the elements in the third row and do this process of the factoring and everything. I could do that too, and it would work. It would help me find the determinant of the matrix, of the 3 by 3 matrix. And I would end up going through and being able to find these minors and then looking at and going further from there. Okay. All right, so another thing to notice is that your symbols alternate, plus, minus, and plus. After you do the factoring, the elements that are outside the parentheses, you're going to find, if you go in order in your row or column, those symbols are going to alternate. And in fact, in all of these matrices, there's a pattern to the symbols. The upper left, that A11 is always plus, and then it always alternates after that, no matter which way you go. So keeping track of your symbols, positive or negative, is going to be important too. Okay, so let's put this together a little bit further. We talked about the minor being that determinant of that leftover 2x2 matrix after you identify an element, when you're looking at focusing on a particular row or column. And then including that sign, you have something called the cofactor. So capital M with the little ij is the minor for element, can't spell today, A sub ij in an n by n matrix, so in a square matrix. The cofactor of A sub ij is capital A, and we do the little row column numbers so we can keep track. And then this first part, -1 to the I plus j, tells us what sign we're using for that cofactor. And if you just remember that it alternates, you can always think about that little array with the plus minus that I wrote down a few minutes ago. Or you can look at the location and just raise -1 to that power of I plus j. So like if it's in row 2, column 3, 2 plus 3 is 5. -1 to the 5th power is -1. So the sign's negative. And then you apply that sign to the minor, and now you have the cofactor. Okay, let's look at an actual example again. Let's revisit our matrix with the 5, -1, 6, 0, 2, -9, 4, 1, 3. And let's find the cofactors of 5, 0, and 3. So we're looking at the elements 5, then 0, and then 3 to do our cofactors. Okay, now keep in mind that the symbols, the signs, are going to be plus, minus, plus, minus, plus, minus, plus, minus, plus in this 3x3, dealing with this 3x3 matrix. Always start with a plus in the upper left in A11. All right, so if we're doing the cofactors of 5, all right, 5 is in the position A11, right? So once you kind of ignore everything else in the same row and column as 5, you can find the determinant of those leftover elements, the little 2x2 matrix. You're going to find the determinant of that. Remember, the little absolute value signs mean you're finding the determinant. So the minor would be that determinant. So 2 times 3 minus 1 times negative 9. So you get 6 plus 9, which is 15. And then the cofactor, a sub 1, 1, is positive 15. That number, that position has a positive. Or if you're not sure, you can say, well, negative 1 raised to the 1 plus 1. So negative 1 squared is 1. So you're going to end up with a positive 15 there. Okay, let's do 0 next. So putting the matrix back up here. And focusing on 0. I'm going to kind of ignore everything else in that row and column. So we want to find, and keeping in mind that 0 is in row 2, column 1. Oops. So looking at my symbols again, I know that I'm going to need a negative symbol in this case. So my minor of row 2, column 1 is me finding the determinant of negative 1, 6, 1, and 3. So I'm going to have negative 1 times 3 minus 1 times 6. So negative 3 minus 6 is negative 9. And then remembering I'm having to use that negative symbol. So then my cofactor at 2, 1 is negative 1 times negative 9, which is 9. Or if you want to think about negative 1 to the 2 plus 1 power is negative 1 cubed, or negative 1. So that's how you know to use that there. All right. And then one more time, we were supposed to do 3 also. So let me rewrite that matrix one more time. Okay, so this time we were doing 3. So we're looking at our symbols. We're going to have a positive again that we're going to multiply by. Okay, so this is row 3, column 3. So the minor of 3, 3. So I get to ignore everything else in row 3 and column 3 when I'm looking at how to do my determinant. So I'm going to be doing the determinant of the matrix with 5, negative 1, 0, and 2 there. So that's going to be 5 times 2 minus 0 times negative 1. It's always nice when you have zeros. It makes things work a lot faster. So you end up with 10. And so then my cofactor, I'm going to end up with positive 1 times 10. So it's going to be 10. Or for that positive 1, you could say, well, negative 1 to the 3 plus 3 power, the I and the j. Negative 1 to the 6th power is 1. Now, if you raise a negative to an odd power, you get a negative. If you raise a negative to an even power, you get a positive. I should put that around there. Sorry. Getting lazy, forgetting my little parentheses when needed. That's not good. Okay, so there you go. So that's the minors and the cofactors. You might be like, well, okay, so now what? How am I going to use all this? Well, once you have all of the cofactors for the particular element, for the particular elements in a row or column of a matrix, you can multiply the cofactors in those elements and then add up the results. Okay, so finding the determinant. This is also called a Laplace expansion. Multiply each element in any row or column of the matrix by its cofactor. Find the sum of these products. So we just need to pick a row or a column. It can be any row or column in the matrix. And then once you pick one, stick with it. Just use that one and stick with it. And then you'll be able to find your determinant. Okay, so I'm keep using that same matrix over and over again, but it's so nice to see how everything works out for us. So let's do the little Laplace expansion on this matrix. I'm going to zone in on row 1. I'm going to use that. So I'm going to have to take the element 5 and multiply that by the determinant of that 2 by 2 matrix for the elements that are not in row 1, column 1. And then keeping in mind that going across you have plus, minus, plus. So I have plus 5 minus negative 1 and then plus 6. Okay, so yeah, those symbols. It's nice like ahead of time to think about what symbols need to go in there. So that way you don't forget later. All right, so then when I take negative 1, that is in row 1, column 2, and then I'm going to multiply that by the determinant of the little 2 by 2 made by the elements not in row 1, column 2. And then for 6, that's in row 1, column 3. And I'll multiply that by the determinant of the 2 by 2 made with the elements not in row 1, column or column 3. Okay, so first one, 5, and then it's going to be times 6 minus negative 9. So 5 times 15, which is 75. And then I've got minus, so plus 1 times 0 minus negative 36. So that's plus 1 times 36, so that's plus 36. And then plus 6 times 0 minus 8. So plus 6 times negative 8, so minus 48. And when you combine those, 75 plus 36 is 111. And 111 minus 48 is 63. And that's the same answer we got at the very beginning of this video when we did trying to track all the various diagonals and find the determinant. But we didn't have to keep track of all these various diagonals. We needed to learn what the minor was and what the cofactor was. But now that we know, I think you'll find this process to be easier to keep track of everything. The only thing to remember is the plus minus signs that need to, go in there that I have in green in this example. But otherwise, I think you'll find that to be Not too bad. Okay, so that's finding a 3x3 determinant. If you're looking at a matrix and you see zeros in there, see, I wanted to show you as much as I could here about what to do, but this matrix, probably better choice would have been to choose column 1 because of the 0 in there. That would have made things a lot faster, because then my middle part would have all come out to 0, because I would have been multiplying by 0, and that would have made it a lot less work. So if you can spot things like zeros and then choose that row or column to use, that can make things so much faster. So that's just a little heads up, a little kind of keep that in mind sort of thing, you know. It'll save you time and energy, that's for sure. I did not save us time and energy, but you can if you decide to do that. All right. Let me go ahead and talk a little bit about determinant theorems to wrap up this video. And then the next video, we're going to kind of continue on for what we've been doing with something called Cramer's rule. So let me just do these determinant theorems and then save a new video for Cramer's rule. And these determinant theorems, if you can use them, if you have a matrix where you can use them, it can save you some time and energy. It can make a big difference. Okay, so like number 1. If every element in a row or column of matrix A is 0. I say matrix A, it can have whatever name, some matrix. If you look at a row and you see all zeros, or if you look at a column and you see all zeros, then automatically you know that the determinant of that matrix is 0. No work needed. For example, let's say you have the matrix 2, 1, -1, 3, 9, -2, 0, 0, 0. Then you know that if that's your matrix A, then you know the determinant is 0 because of that lovely column there that's all zeros. No work needed. If you really wanted to do the work, you could, but think about it. Let's say you picked that third column to use when you're trying to find the determinant. Well, since all of column 3's elements are zeros, you're going to end up multiplying each step by 0. So it all is going to come out to 0. Okay, number 2. If the rows of matrix A are the corresponding columns of matrix B, I cannot spell today for some reason. I know how to spell, it's just as I'm writing, I want to skip letters and move on. Then the determinants are the same. Okay, for example, let's say you have matrix A has -1 and 3 in the first row and -2 and 9 in the second row. So it goes this way, this way. And let's say you have matrix B that instead of -1 and 3 being the first row, -1 and 3 is the first column. And instead of negative 2 and 9 being the second row, negative 2 and 9 is the second column. Watch what happens when you find the determinants. Okay, so first one you get negative 3. And we expect to get negative 3 in the second one as well. Because notice that you end up multiplying the same numbers together and all that. So there you go. Then you know, like in that case, you know that they both should come out with the same determinant. Number 3. If any two rows or columns of matrix A are interchanged to form matrix B, then the determinant of B is the opposite of the determinant of A. In other words, one's the negation of the other. So let's say matrix A has negative 9 and 7, 2 and 6. And let's say to make matrix B, let's say we swap column 1 and column 2. So column 1 becomes column 2 becomes column 1. If I wanted to, I could swap the row 1 with row 2, it's, whatever. As long as you can pick any two rows or columns and swap them. Like 2 rows, swap them, or 2 columns and swap them. Interchange them. All right, let's look at what the determinants are. So in the first one, you end up with, you have negative 9 times 6 minus 2 times 7. So you got negative 54 minus 14, which is negative 68. In the second one, you have 7 times 2 minus 6 times negative 9. So that's 14 plus 54, which is positive 68. So the determinants are opposites. All right, number 4. Let's say you take a row or column in matrix A and multiply every element just in that row or column, whichever one you pick. You just pick one, and you take every element and whatever you picked and multiply by a real number k. It has to be a real number. For the new matrix B, the determinant is going to be the same thing as taking the determinant of A and multiplying by that constant, that real number. All right, so say for example you have matrix A with negative 1, 5, negative 2, and 3 there. And we're going to use 8. And I'm going to multiply column 1 by that to get, it doesn't matter which row or column, but I just picked column 1. So I end up with negative 8 and 40 in column 1 there for matrix B. The negative 2 and 3 are still the same. But let's look at our determinants. Negative 3 plus 10 is 7. Then for B, the determinant, I've got Negative 24 plus 80, which is 56. Notice 7 times 8 is 56. So if you take the determinant of A and multiply by that K, which is 8, you get the determinant of B. All right, three more theorems. Number 5. If 2 rows or 2 columns of matrix A are identical, then the determinant is 0. Okay. Let's say I have this 3 by 3. Matrix. Notice that row 1 and row 3 are identical in this 3 by 3 matrix. I'm going to go ahead and use column 1 to find the determinant. So I got to remember my signs. I've got what? Plus, minus, and plus. So I'm going to have 2, then the determinant of 4, 5, 3, and 7, minus 1, determinant of 3, 7, 3, 7, plus 2, determinant of 3, 7, 4, 5. So you might notice the patterns here of what's happening. So 2 times 28 minus 15, so that's 2 times 13, which is 26, minus 1 times 21 minus 21, so minus 0, plus 2 times 15 minus 28, so plus 2 times negative 13, so minus 26. So notice we end up with like a multiple situation here where you can see where 0 is coming out of it. You got that 0 in the middle because that middle matrix, the middle matrix there had identical rows. And then the first and last matrices just had rows that were swapped. So remember what we said about swapping or interchanging rows? The determinants end up being opposites. And that's what happened there. You had a 26 and a negative 26. And all of that comes out to 0. All right, number 6. Getting there, 2 more. Let's see. The determinant does not change when a column or row is changed by adding to a multiple of another column or row. So you take a constant times another row or column or whichever one you're dealing with. And if you add that to change the row, it's not going to change your determinant. Okay, so let's say you have matrix B. With 2, 1, 7, negative 4, 0, 8, 6, 5, 21. I think I'm going to use column 2 for this one and find the determinant of B. So I got to remember minus, plus, and minus for that one. So negative, whoop, black again. Negative 1 times determinant of negative 4, 8, 6, 21, plus 0, determinant of 2, 7, 6, and 21, then minus 5, determinant of 2, negative 4, 7, and 8. All right, so I'm just like double checking, making sure I didn't lose track of or write down the wrong number anywhere. Yeah, the middle one I know is 0. So I don't have to do anything extra there. Okay, so negative 84 minus 48, 12. That's negative 132. So I'm going to get 132, and that's 0. 14, 44. So what, negative 220? So I end up with negative 88. Now, what if I decide to take that same matrix and do a new one? Let's say I do, call it C, where the first row is the same, second row is the same. But how about we take, how about we take the first row times negative 5 and add that to the third row. So I'd have negative 10 plus 6 is negative 4. Negative 5 plus 5 is 0. Negative 35 plus 21 would be negative 14. I'm doing this on purpose because I want those zeros in there. Zeros make things so much easier. And I'm going to once again use that second column. But this time, when I go to do my determinant, I don't even need to worry about those zeros. I do need to keep track of my sign right there. But I know I'm going to have negative 1 times the determinant of whatever negative 4, 8, negative 4, and negative 14 turns out to be. I don't have to worry about the zeros because that's all going to come out to 0 anyways. So I've got negative 1 times, what, 56 minus negative, so plus 32. So negative 88. Comes out the same. That's what this whole theorem was saying, number 6 was saying. I took a multiple of row 1, so I multiplied it by negative 5, and then I added that to row 3 and made that new matrix. When I found the determinant of that new matrix, it ended up being the same as the determinant of the old matrix. And you don't even have to use the, like I used the second column again, only because I liked using the zeros. But you could find your determinant any way you want, and it's going to come out the same. Like you can use row 1, you could use column 3, you know, whichever row or column you want. You don't have to use the same row or column as you did in the first computation. And it's still finding the determinant. So then that's still going to get you the same result. All right, one more. Number 7. Let's say that matrix A is in triangular form. With only zeros either above or below the main diagonal. Just has to be one or the other. It doesn't have to be both. then our determinant of matrix A is really easy peasy. It's the product of the elements on the main diagonal of A. Okay, for example, let's say A is the matrix 4 by 4. 1, 2, 5, 8. Don't let it scare you though, because I'm going to be demonstrating this rule. Now you could go through and find the determinant using the same process we did earlier. Pick a row or column you want to use, and then go through and then, multiply each element in that row or column by the determinant of that leftover matrix of the elements that are not in that row and column. So you could do all that, but you don't have to. You can recognize that underneath the main diagonal, we have these zeros. So the main diagonal is right here. So either above or below, if it's all zeros, then you can find the determinant by just multiplying the numbers in that main diagonal. So we have a 1, a 4, a -2, and a 9. I accidentally marked over the negative there. So multiply those together. 4 times -2 is -8. -8 times 9 is -72. And there's your determinant. All done. If you wanted to go through and verify this and prove it, you can. Like, you could take that matrix right now and actually work out the determinant, and you would get the same thing. Like, let's say you went ahead and just used column 1 with the 1 and the zeros, and then found, took 1 times your determinants from the remaining little matrix there. You would get -72 still. It would all work out very nicely. So there you go. All right. Well, that's all I want to do for this video. Like I said, I'm going to jump into Kramer's rule in the next video. I feel like that's a little long too. So there you go. Hope you enjoy finding determinants, and I will see you again very soon.